Welcome to today's deep dive. You probably interact with this invisible architecture every single day.
Oh, absolutely. I mean, whether you're, checking your bank balance or just swiping on an Android phone.
Or even reading a PDF, right?
Exactly. Yeah.
Well, back in 1991, a team at Sun Microsystems started building a programming language. And it was actually supposed to control interactive cable television boxes.
Right, like smart remote controls and home
Yeah,
appliances.
which is wild to think about. But then 4 years later, they pivoted, released it to the public, and somehow that exact same core technology ended up, running the back-end processing for global mega banks.
Empowering massive big data clusters.
Right, and operating the vast majority of mobile phones on the planet.
It's honestly one of the most fascinating architectural pivots in software history. I mean, they engineered a solution for a hardware landscape that didn't really exist yet.
But the smart appliances.
Yeah, exactly. And in doing so, they accidentally solved the biggest software bottleneck of the impending dot-com boom, which was cross-platform portability.
So today, we are tearing down the engine of the Java programming language. We got a comprehensive source text breaking down the fundamentals, and our mission isn't to teach you how to write a Hello World app or, teach you syntax.
Right. No coding required today.
No coding required. We want to understand the underlying engineering decisions, the structural mechanisms that make a language released in 1995, the invisible infrastructure of the modern digital world.
And at the absolute core of this engine is a four-word philosophy that fundamentally changed software design.
Write once, run anywhere. WORI.
Yes. Write once, run anywhere. And to really appreciate how radical that was, you have to look at the development nightmare of the early 90s.
Set the stage for us. How bad was it?
It was, well, if you were writing a program in C or C++ Air, your code had to be compiled directly into machine code. And that machine code was tied to a specific physical architecture.
So the actual hardware inside the computer.
Yeah. Right. So say you compiled your software for an x86 processor running Windows. If you wanted to port it to a SunSpark station or an Apple Mac, you couldn't just, move the file over.
Because they speak different languages at the hardware level.
Exactly. You had to account for entirely different memory layouts, different hardware instructions, and just different compiler quirks.
Which means you're basically maintaining 3 or 4 parallel code bases just to release one piece of software to the market.
It was a massive waste of resources.
So Java's bypass for this was to just stop compiling to the metal entirely, right? Like instead of compiling to machine code, the Java compiler translates your source code into something called bytecode.
And bytecode is really the stroke of genius here. It's an intermediate, highly optimized set of instructions, but it isn't tied to any physical processor on Earth. It's basically machine code for a ghost machine.
A ghost machine, I like that. The Java Virtual Machine, or JVM.
The JVM.
So is the JVM basically like a universal translator? Like you speak in Java, it turns into this intermediate bytecode language, and then the JVM translates it to whatever local hardware language is needed on the spot.
That is a perfect analogy, yes. The JVM is an abstract computer running inside your actual computer. So when you run a Java app, you're really launching the JVM on your host operating system, and the JVM executes that bytecode.
Okay, so because Sun Microsystems built, a JVM for Windows, and a JVM for Linux, and a JVM for Mac.
Developers only have to compile their code one single time. The JVM handles that final mile of translating the bytecode into the local hardware instructions.
Okay, wait. Hold on, though.
Yeah.
If you're layering an abstract software computer over the physical hardware, and you're translating instructions on the fly, aren't you inherently introducing a ton of latency?
You are. Yeah.
Because adding a middleman interpreter usually destroys execution speed. How did Java not just crawl to a halt in production environments?
Well, you're right. In the very early days, interpreted Java was noticeably slower than natively compiled C code. It was a real problem.
So how did they fix it?
They solved the compilation bottleneck without abandoning the JVM by introducing something called the JIT.
JIT?
Right, the just-in-time compiler. So the JIT operates inside the JVM, but it doesn't just blindly translate bytecode line by line over and over again. It actually actively profiles the application while it's running.
Oh, interesting. So it's looking for, like, the hot spots in the code, the methods or loops that are being executed thousands of times a second.
That is exactly the mechanism. When the JIT compiler identifies a hotspot, it intercepts that specific chunk of bytecode and compiles it all the way down to native machine code right on the fly.
Wow.
And then it caches that highly optimized native code in memory. So the next time the program hits that function, it bypasses the interpreter completely.
And just runs the native instructions at full speed.
Exactly. The application literally optimizes its own performance at runtime based on how the user is interacting with it.
That is such a dynamic approach to performance. I mean, it's essentially adapting as it goes.
It is. But there's another layer to this cross-platform stability that goes beyond just translating instructions, and that's something called architecture neutrality.
Architecture neutrality.
Yeah. In C++, say, the physical size of your data types could actually change depending on the hardware.
Wait, what do you mean? Like the actual size of the data?
Yeah. An integer, for example, might take up 16 bits of memory on an older system, but then on a newer system, it might take up 32 bits.
Oh, I see where this is going.
Yeah, it was a nightmare for memory allocation. If you wrote a program assuming an integer took up 32 bits and then you ran it on an older machine where it defaulted to 16 bits, you would instantly hit memory corruption or a buffer overflow. It would just crash.
So Java eradicated that dependency.
Completely. A standard integer in Java is strictly 32 bits. A long integer is 64 bits, period.
So it does not matter if you're running it on a supercomputer or a smart refrigerator.
It will always be exactly the same size.
So it's kind of like a recipe where a cup of flour is exactly the same measurement in every kitchen in the world, guaranteeing the cake always comes out the same.
That's a great way to put it. By rigidly enforcing the exact dimensions of the data, Java guarantees that the program's memory footprint behaves predictably across every architecture on the planet.
Which is huge.
It's massive, and that rigid standardization is a huge theme in Java's overall design. I mean, to drive adoption back in 1995, the creators modeled Java's syntax on C++ because they needed it to feel familiar.
Right, to all the developers who are already working in the industry.
Exactly. But they ruthlessly stripped out the C++ features that were notorious for causing system crashes.
Okay, but taking away features like, what does the source say? Multiple inheritance through classes and operator overloading.
Yeah.
That feels less like simplifying the language and more like putting a straitjacket on the developer. You know what I mean? Like, if they removed all these advanced tools, does that mean Java is essentially C++ with training wheels?
Ugh. I wouldn't call them training wheels. They're really more like guardrails.
Guardrails, okay.
Yeah. It wasn't about dumbing the language down. It does remove some raw flexibility, sure, but it enforces a very specific architectural discipline, object-oriented programming, or OOP.
Okay, OOP. Let's break that down because our source makes it clear this is fundamental to how these massive enterprise systems are structured.
Right. So by restricting how classes inherit from one another, Java forces developers to rely on the 4 core pillars of object-oriented programming to build modular, maintainable systems. Everything is an object that combines data and behavior.
And those 4 pillars are abstraction, encapsulation, inheritance, and polymorphism.
You got it.
So abstraction is essentially hiding the complex implementation logic behind a simple interface.
Right, like you don't need to know how the combustion engine works to press the gas pedal.
Exactly. Then you have encapsulation, which is about protecting the state of the object. So instead of letting any random part of the program directly modify an object's data, you lock the data down.
Yes, and you only allow access through specific controlled methods, getters and setters.
Because that prevents other parts of a massive application from accidentally corrupting the internal state of your objects, right?
Precisely. And then inheritance allows you to create hierarchical relationships to reuse code.
So if you build a baseline, say a user class with login functionality, you could just create an admin class that inherits all that baseline code but adds extra privileges.
Exactly, without having to rewrite the login logic all over again.
Makes sense. But polymorphism seems to be where the architecture really gets powerful.
Oh, absolutely. Polymorphism allows you to write code that can process different types of objects through the exact same interface.
Okay, think of a financial trading platform.
Good example.
You might have an interface called payment processor. You can write one core function to process transactions and pass it a credit card object, a crypto wallet object, or a bank transfer object.
Right.
And because they all implement the payment processor interface, the system just treats them uniformly.
Exactly. You can plug entirely new payment methods into the platform years later without ever touching the core transaction code.
Which is wild.
That modularity is exactly why enterprise software relies on Java. But, going back to your point about the language acting as a straitjacket or having guardrails, the most consequential feature Java stripped out of C++ wasn't multiple inheritance.
What was it?
It was explicit pointers.
Right, pointers. In C or C++S, the pointer gives the developer direct access to physical memory addresses on the hardware.
Which means you can tell the program to go to a specific hexadecimal memory location and just read or overwrite whatever is there.
Which sounds incredibly powerful for, like, writing operating systems.
It is.
Yeah.
But it is a massive security vulnerability for applications. Because if a program can arbitrarily point to memory addresses, a malicious actor can exploit that.
Oh, right.
They can feed a program more data than it expects.
A buffer overflow attack.
Exactly. And overwrite adjacent memory that's holding executable code, forcing the system to run malware.
Wow. Okay, so by removing explicit pointers, Java just completely sealed off direct memory access.
Completely. A Java program literally does not possess the grammatical capability to point to a raw memory address. It can only reference objects within the JVM sandbox.
And the JVM sandbox acts as an isolation chamber.
Yes. The operating system doesn't fully trust the Java program, and the Java program doesn't interact directly with the OS. It goes through the JVM.
And there's also the bytecode verifier, right?
Yeah.
Like before the JVM even executes a piece of bytecode, it runs it through this verifier.
Right. The verifier analyzes the data flow, ensures no memory access violations are going to happen, and confirms all the types match up. If the bytecode looks malicious or even just malformed, the JVM straight up refuses to run it.
That is some serious structural security.
It really is.
And that security is paired with structural stability, specifically through how it handles memory allocation. Because in older languages, developers had to manually allocate memory when they created a data object, right?
Mm-hmm. Yes, and more importantly, they had to manually free that memory when they were done with it.
And if you forgot to write the code to free the memory,
You created a memory leak. The application would slowly consume all the available RAM until the entire server was crashed.
so how did Java solve that? Because obviously Java servers don't just crash constantly from memory leaks.
They solved it by implementing strong automatic memory management, specifically garbage collection.
Okay, so garbage collection is basically like having a little robotic Roomba constantly running in your computer's memory, sweeping up data you aren't using anymore so the system doesn't crash.
That is exactly what it's like. The programmer creates the objects, but the JVM takes over the responsibility of destroying them when they're no longer needed.
But wait, how does the garbage collector actually know what is safe to delete? Because if it accidentally deletes an object the program is still trying to use, doesn't the whole system collapse?
It would, yeah. So the JVM uses a mechanism based on what's called reachability. You can think of it like an auditor checking a complex corporate ledger. The garbage collector starts at what are called GC roots. These are usually the active threads and local variables that are currently executing. And it traces every single reference, mapping out every object that is still connected to the active execution of the program.
I think our source called this a mark-and-sweep process.
Yes. It traverses the memory graph, literally marking every object it can reach. Once it finishes tracing all those active connections, it looks at the entire memory heap.
And any object that wasn't marked.
Is considered unreachable. The program literally has no way to access it anymore.
Oh, wow.
So the garbage collector sweeps through, liquidates those disconnected objects, and reclaims the memory for the system.
It just completely eliminates human error from memory management.
It really does. And if something does go wrong at runtime, say, I don't know, a network connection drops or a database server goes offline, Java enforces strict exception handling.
Which is another one of those vital guardrails.
Exactly. If an error occurs, Java generates an exception object that encapsulates the details of that error. The language forces developers to write structured try-catch blocks around risky operations.
So if the database connection fails, the program catches the exception, logs the error, and executes a fallback plan.
Right, rather than just crashing to the desktop and taking the whole application down with it.
Okay, so stepping back, we've basically mapped out an architecture that is highly secure, isolated from hardware quirks, self-optimizing via the JIT compiler, and immune to manual memory leaks.
Pretty impressive for 1995.
Seriously, it sounds like the perfect foundation for scaling up. And scaling up in the late 1990s meant one thing: the internet.
Yep. Java was fundamentally designed for networked environments. One of its really native capabilities is multi-threading.
And a thread is just an independent path of execution within a program, right?
Exactly. Java allows developers to spin up multiple threads concurrently, and they're managed directly by the JVM.
Which is crucial, because if you're building a web server, you can't have the entire application freeze every time a single user requests a large file download.
Right. Multi-threading allows the server to spawn a dedicated thread just for that user's download, while the main application continues listening for thousands of other concurrent requests.
But doesn't handling concurrency introduce complex challenges, like uh, race conditions, where two threads try to modify the same piece of data at the exact same time?
It definitely does. But Java provides robust synchronization mechanisms built right into the language. It allows you to lock objects and prevent data corruption across threads.
Wow. And beyond just running multiple threads on one machine, Java also pioneered early distributed computing protocols, things like RMI.
Remote method invocation, yes.
How does that work?
Well, RMI allowed a Java application running on a server in New York to call a method on a Java object living on a server in Tokyo. It could pass parameters to it and receive the result almost as if that remote object was sitting in local memory.
That's crazy.
It abstracted away all the incredibly complex socket programming and network serialization that's usually required to make two separate machines talk to each other.
Okay, wait. I have to push back here.
Sure.
You're calling this a simple language.
Right.
But if a program is managing simultaneous tasks, communicating with other computers globally, and, we haven't even talked about reflection.
Reflection, yes.
The architecture allows a running Java program to dynamically inspect its own classes, its own methods, and variables at runtime. It can instantiate objects and invoke methods that it didn't even know existed when the code was originally compiled.
It's essentially metaprogramming.
Right.
Yeah.
So how does that qualify as simple?
Well, the distinction lies between the strictness of the syntax and the dynamism of the runtime environment. The syntax and rules are simple, but reflection is an advanced capability that allows the applications themselves to be incredibly complex.
Give me an example.
Well, it's what allows modern massive frameworks like Spring to exist. In an enterprise system, you don't want to hard code every single dependency.
Right, dependency injection.
Exactly. Using reflection, a framework can scan your application at startup, discover all the classes you wrote, automatically wire them together, and inject the necessary database connections or security protocols without you having to write all that tedious boilerplate wiring code.
Oh, I see. So the system adapts dynamically based on the configuration it just reads at runtime.
Exactly.
That dynamic capability, combined with the extreme portability of bytecode, brings us to the real-world footprint of this language. The design choices Sun Microsystems made decades ago basically dictate the technology stack of the modern world.
Without a doubt. I mean, the most visible implementation is Android.
Right, Android development.
The entire Android operating system application layer was built around Java. When you swipe open a banking app on an Android device, a specialized virtual machine is running compiled Java code.
But the true dominance of Java seems to be in the enterprise backend. Like we said earlier, financial institutions like Goldman Sachs and Citigroup rely heavily on Java for their core processing systems.
And based on everything we've talked about, it's pretty obvious why.
Yeah, if you're processing billions of dollars in high-frequency trading, you cannot afford a memory leak.
No.
You cannot afford an unhandled exception just crashing the server. You knew the predictable garbage collection, the strict type safety, and that fixed architecture neutrality.
The JVM provides a fortress of stability for systems that have to run flawlessly for years without rebooting. And that same stability is exactly why the foundational tools of big data are written in Java.
Like Apache Hadoop and Apache Spark.
Yes, the frameworks that process literally petabytes of data for global analytics, they are all JVM-based.
And Hadoop is really the ultimate validation of that write once, run anywhere philosophy, isn't it? Because in big data, you don't move petabytes of data to your processing code. The data is just too heavy.
Too heavy, exactly. You have to ship your code out to the thousands of server nodes where the data actually lives.
Right. And because Java compiles to platform-independent bytecode, Hadoop can take a tiny Java function, distribute it across a cluster of thousands of totally diverse Linux machines, and the JVM on each node just executes the code locally against its slice of the data.
It's brilliant. The architecture that was originally meant for cable boxes perfectly scales to global data centers.
It's honestly a masterclass in software engineering and foresight.
Yeah.
The JVM, the JIT compiler, the mark and sweep garbage collection, these aren't just technical details. They are the invisible infrastructure supporting the digital economy.
They turned the chaotic, fragmented landscape of 90s hardware into a unified, programmable platform.
It's amazing. But before we wrap up today's deep dive into the architecture of Java, I want you to consider the implications of that reflection feature we discussed.
Oh, yeah.
A program possessing the capability to inspect its own structural composition, analyze its own methods, and dynamically invoke new behaviors while it is actively running. As we move rapidly into an era of artificial intelligence and software that constantly learns and iterates on its own logic, I want you to look back at the mechanics of reflection.
It's a very relevant concept right now.
It really is. The idea of a program being structurally self-aware enough to peer into its own blueprint was engineered in the mid-1990s. It raises a fascinating architectural question. As software continues to optimize itself, how much further can code evolve when it is given the tools to look in the mirror?
The gap between dynamic runtime reflection and autonomous software generation is narrowing every single day.
Something to think about the next time you interact with the invisible architecture all around you. Keep questioning the foundations of the digital tools you rely on. We will catch you next time.